I'm helping with some research, needed something, so I had to go to my car and get it. Oh, and we are recording now, so let's get the finally, okay. And maybe even turn on the projector. The only announcement I know about, and this is just sort of a minor one, I saw on the board this Friday, I think at 10 o'clock in the morning, on the Birmingham East Campus, that's the A.G. Gaston building, they're going to have a performance, I think it's UAB Theaters, is presenting The Taming of the Shrew. And I'm sure they would love to have a good crowd there. I don't know if you're particularly into that. It sounded, I read the little blurb on it, and it sounded like they have fiddled with it. Everybody, likes to be creative with things like this. Taming of the Shrew, I don't know if you remember. It's Shakespeare, it's a comedy, and it was supposed to be the very difficult woman, and the guy's trying to tame her, and she's not very tameable. Way back, you wouldn't remember this, Richard Burton, you wouldn't remember him, and Elizabeth Taylor did a movie on it, and I think maybe they both won Oscars on it. They later or then were married or something. But anyway, very famous Shakespearean play. But since they're going to be very creative about it, they have the guy being difficult and the woman trying to tame him. And so anyway, if you want to see it, it's going to be Friday, I think 10 o'clock, A.G. Gaston building on the Birmingham East Campus. Can't think of anything new for us. I've got at least a paper in and a test in from each of you, so keep those coming. All right, good deal. And let's see. All right, we're not going to hit this slide for a while, so let's pick up where we left off last time. We're talking about the method of partial fractions. When do we use this method of partial fractions? When is this technique we use for our integration? When you have what kind of an integrand? Rational function. What's a rational function? Rational means? What's the first 5 letters? Ratio. So it's a division. And what are the two things being divided? By the way, rational numbers are numbers written as ratio of two integers. Rational functions, ratio of two polynomial functions. Okay? They are functions of polynomial functions. Okay? Now, what's true about polynomial functions? They're what? They potentially, not always, but potentially could be factored and things like that. So, that's what we're dealing with. Now, in order to do the method of partial fractions, though, this has to be what they call a proper rational function. What do we mean by that? What? Okay, in a numerical fraction, that would be the case. The denominator is larger than the numerator. With polynomials, what needs to be? It's the same kind of concept, but what has to be bigger in the denominator than the numerator? The degree, yeah. The maximum exponent, okay? That has to be larger in the denominator. For instance, is this, let me get my pen activated here, okay? Is that a rational function? Yes, it's a ratio of two binomials, two polynomials. Is it a proper rational function? Okay? The degrees are the same. That would be like 7 over 7 is a proper number. Proper fraction, that should be 1. Okay? So this is a proper rational expression. Now, how did we, this is what we did last time. I know it was a long time ago. That's Wednesday. How do we get that into rational form? I know many days ago. Okay. What if we had what if that had been a fraction? How would you get that to be a proper fraction? Or, let me say, a mixed number, a whole number with a proper fraction. Divide. Yeah? How do we get this? Divide, okay? Divide the denominator into the numerator. Okay? And how many times will that go? Remember how to do our long division of fractions? X will go into X. X will go into X. How many times? One time. Okay. And then you multiply. What will you do here? 15 into 22. That would go one time. Then you multiply. 1 times 15 is 15, right? So 1 times x minus 5 is x minus 5. And then you do what? Subtract, which is the same as change signs and add. That gives you 3. So this would be plus 3 over x minus 5. Now you have a polynomial 1 plus a proper rational function, right? So that would be the first step. Get your rational function, make sure it's proper. If it's not proper, divide and make it proper. Okay? Now, so let's first suppose that P over Q is proper. That's the first thing. And we've just been describing how to do it. That means the degree of the numerator is less than the degree of the denominator. Not the same, not greater than, less than. Okay? So let's first suppose it is proper, and that the denominator, Q of x, okay, factors as a product of distinct linear factors. So this Q of x would be, got a sneeze, sorry. I'm just going to write it over here. This thing would be P of x in the numerator, and this denominator would be x minus a1 times x minus a2 times x minus a3 times times x minus a to the n. So you have n linear factors. Okay? Now, and those roots, a1, a2, a3, a4, and so on, are all distinct, none repeated, all distinct. And the degree of P is less than n. That makes it proper. So they're repeating themselves here. Then there is a partial fraction decomposition that you can do, and this P of x divided by Q of x is going to be some a1 over x minus a1 plus a2 over x minus a2 plus a3 over x minus a3 plus plus a sub n over x minus a sub n. Okay? Now, the capital A's are just integers. Just integers. The little a's are your factors, are your roots. Okay? They use the same letter, but one capitalized, one little. They have no relationship to each other except they go together. but they have no relationship. Okay? This is called a partial fraction decomposition. Okay. So let's actually do it. See if we can. All right. Here is 5x squared plus x minus 28 over, now they didn't tell you what the denominator was, they factored it for you, aren't they nice? X plus 1 times x minus 2 times x minus 3. Okay? Can you break that into a A1 over x plus 1 plus A2 over x minus 2 plus A3 over x minus 3. Now, again, why they did this, the subscripts on the A1, 2, and 3 have nothing to do with the x plus 1, x minus 2, x minus 3. That just happens to be that way. It could be anything. Okay? So, if that is findable, is that a good way to say it? How would we go about determining it? What's messy about that expression? We call this the method of partial fractions. And we love our fractions, don't we? But they're just a little messy to work with, aren't they? It'd be nice if those were just linear functions. Wouldn't that be nice? Yeah. Well, how, with an equation like this, how could you deal with getting rid of those denominators? Because this is an equation. Multiply both sides of the equation by the least common denominator, which is this big one over here, right? So let's multiply everything on both sides by x plus 1 times x minus 2 times x minus 3. Okay? Multiply this one by x plus 1 times x minus 2 times x minus 3. Multiply this one by x plus 1 times x minus 2 times x minus 3. And multiply this one by x plus 1 times x minus 2 times x minus 3. Running out of room, but we did it. Okay? Now, notice on the left-hand side, that one goes out, right? This one goes out, and that one goes out. So that leaves us with 5x squared plus x minus 28. Nice, beautiful number there, right? Okay? Equal to, well, what happens over here? This one, the x plus 1's go out, right? Divide away. So that leaves us a1 times x minus 2 times x minus 3. Plus, here the x minus 2's go out, and that would be a2 times x plus 1 times x minus 3, right? You do the last one for me.
Plus A3.
Yeah, plus A3. X plus 1 times x minus 2. Still running out of room, okay? Because the x minus 3's go out, okay? All right. Now, we could, if we wanted to, multiply these two together and multiply by a1, and multiply those two together, multiply by a2, multiply those two together, multiply by a3. Each of these terms don't have x squared in it. And then you know that a1 plus a2 plus a3 is going to equal 5. And we could do that, you know, and then whatever our x terms were, they're going to have to add up to be a 1. And whatever our constant terms are going to have to be, they're going to add up to be a negative 28. And then you have 3 equations, 3 unknowns. You've gotten rid of the x's, basically, but now you have a's. And then you have to solve them. And those aren't particularly easy to solve. There's an easier way to do it. And it really doesn't seem fair, but it works. So do it. Let's just assume that x is equal to 2. Because this equation should be true for any value of x, right? Let's just assume it's true for x equal 2. And notice what happens here. If x equals 2, what does this become? So that whole term disappears. And x equals 2 doesn't. Goes to 0. And then you have x equals 2. Let's go back here. So for x equal 2, we have 5 times 2 squared, which is that'd be 4, right? 5 times 4 is 20, plus 2 is 22, minus 28 would be a minus 6, right? By that? Yes? Okay. Is equal to, this one went away, and this one went away, so you have a2 times, if x equal 2, that would be 3, right, times negative 1, right? Do you see that? Don't think we need the calculators yet, but let's see. This gives you negative 6 is equal to negative 3 a2. So what is a2 equal? Positive 2. That wasn't too bad, was it? Now, since that worked so well, let's pick another value for x. Say again? Yeah. 3. Okay, sounds good. X equals 3. What does the left-hand side give you then? $45 plus 3 would be 48, minus 28 would be 20, right? And at x equals 3, that one goes to 0, right? This one goes to 0, and you're left with a3 times 3 plus 1 is 4, okay. And 3 minus 2 is 1. All right, doing hard math this morning. So this is equal to 4a3. Well, guess what a3 is going to be then? 5. Very nice. Okay. Want to try it one more time? What might you choose? Not 1. You could choose 1. That's a perfectly good number to choose, but it's not going to help you a lot. Choose a negative 1. See? Then that goes to 0, and that goes to 0, so you're just left over here. So when x is negative 1, what is your left-hand side? X is negative 1. Say again? Okay, you would have a 5 minus 1 would be 4, minus 28 would be minus 24. Very good. Is that what you said? I thought it was. Yeah. I don't hear well. Okay. These two terms, a2 and a3, they leave the picture because x minus 1 is 0. So you're just left with a1 times x equal minus 1. That would be a minus 1 minus 2 is negative 3 times minus 1 minus 3 is negative 4. So minus 24 is equal to 12a1. So what would a1 be?
2.
Say again?
2.
How about negative 2? Got it? Okay, negative 2. Okay, well, let's see what we got. We got 5x squared plus x minus 2, minus 28 over x plus 1 times x minus 2 times x minus 3 is equal to our a1, a negative 2 over x minus 1, right? Takes a while for this to catch up. Plus 2 over, because a2 was 2, over x minus 2, right? And then we had a plus 5 over x minus 3. All right? And they just sort of voila'd it and said, here's what we got. And they put the minus out in front, minus 2 over x plus 1. What happened to the plus sign? Okay, plus 1, plus 2 over x minus 2, plus 5 over x minus 3. Hey, that looks a little simpler than this. Especially if I was trying to integrate this. Okay? And I would have a hard time integrating that. But guess what if I tried to integrate this? What would this be? This term here. Yeah. And how the derivative of 1 over x? Log x. So this would be a minus 2 times log x plus 1, plus 2 times log x minus 2, plus 5 times log x minus 3. You can almost do it, right? Buy that, or is that all magic? Huh? Oh, okay. I think I must be Mr. Slomanex today, you know. Pretty good. Actually, I had a physics professor at Georgia Tech. I can't remember which term I had him. I think it was my first term. Sophomore year, first physics course I took there, engineering physics. Had them 8 o'clock in the morning, big lecture room, probably 220 to 200 students sitting back there. And he was down there, and his name was Professor Ewald. He taught with monotone out like this, and never changed the speed or tone or anything else. And the people were flopping like flies, you know. And then he would be just rambling on, and he'd lift up his physics book and have a quick side, drop it down on the table or the platform. And I was in there, and that came up, and he was in the same line of thought that sometimes I found it necessary to demonstrate the law of gravity, you know. Never changed his tenor or anything. His cadence, everything was just like this. The whole 50 minutes, it seemed like 50 hours, you know. But that was, and they called him the Sandman. Okay. Georgia Tech had strange names for profs. Okay. So we've just shown how we go about doing this. Okay? Once we found the partial fraction decomposition, which we just did, we can then integrate the individual terms, and it's generally a piece of cake. Okay? So let's go to example 1, and I think this is part of example 1 here, so let's go down here and clear the ink and evaluate this. The integral of dx over x squared minus 7x plus 10. Now, what haven't they done for you this time that were so nice to have done the last time? They factored that denominator for you. This time you have to factor it. If it's factorable, is it? How? Second? Is that factorable? You want a quick review of factoring? I like to factor by, when you multiply two binomials together, you call that foiling, right? I like to unfoil. So I take that first one and say, what's the only possible factorization for x squared? X times x. So put those in place. Now, I don't spell well when I unfoil, so I look next at the sign of the last term. It's a what? Which means these two signs have to be the same. Okay? So look at the middle sign here. So they both have to be negative. So they'll be negative, negative. Okay? And then we want two numbers that multiply to be 10 and add to be negative 7. 5 and 2. Okay. That wasn't too bad, was it? Maybe. Okay? Now, oh, and by the way, how would you go about that if you didn't have partial fractions? Remember what we did before, completing a square and that kind of stuff, and then doing some, probably a tangent substitution and stuff. Oh, I don't want to do that. Let's try this one. Should be a little easier, shouldn't it? We like easy, right? Okay. No, you don't. You're a hard worker. Okay. So, what we want to see, does this thing, and that fraction is now 1 over x minus 5 times x minus 2, does that equal some a1 over x minus 5 plus a2 over x minus 2? Is there a way to decompose that into partial fractions? We sure hope there is. What would be our first step? Multiply by what? The what? The least common denominator, which is? Yeah, x minus 5 times x minus 2. Multiply this by x minus 5 times x minus 2. Multiply this by x minus 5 times x minus 2. Okay? Here they both go out. Here the x plus minus 5s go out, and here the x minus 2s go out. So, is it helpful to write down that equation that's left, or can you go from there? Okay? What would you do to go from there? Pick a number, yeah. Okay, you chose 3. Any particular reason? I mean, it's a perfectly good number.
Because that way, 3 minus 2 is 1. That's easier.
What's even easier? 0! Okay, what might you choose x then to be? 2. Okay, let's choose x equal 2. 3 would work. It really would. You'd have 2 equations, 2 unknowns. Yeah, you can do that, but you're a hard worker. I told you that, right? Easier is choose x equal 2. Okay, the left-hand side becomes what? 1. It doesn't change. Right-hand side becomes?
0.
The first one goes 0. The second one is? Second? A2 times No, not 0. What was x equal? That's why I wrote it down.
1. No. 2.
All right, cleverly disguised there, okay? So you plug in x equal 2 there, and you get what?
Negative 3.
-3. So this implies that A2 is equal to
3. Negative 3. 1/3. Negative 1/3.
-1/3. How good, okay. Multiple choice here, okay. Now, -1/3, right?
Yeah.
All right, good deal. Want to try again?
Yes.
What would be your next yes?
5.
X equal 5. Very good. What does the left-hand side become?
Wait, what was it?
What does the left-hand side become?
1.
1. It stays 1. It's not affected by X, okay? And the right-hand side becomes?
A1
A1 equals
equals
3? Times 3, okay. And then the second term goes to 0. So that's A1. Yeah, I left off on 1. Which implies that is equal to 1/3. All right. So now we've got our partial fraction decomposition. So we rewrite this integral to be the integral of, I'm going to need more room, so is it all right to erase some of that? What's that? All right, too? Can I erase this part here? That? Okay, let me erase that. In fact, I think I can erase it all except just what the A1s are, A's are, A1 and A2. I hope I did it right. Okay. So that will be I'm going to write it down here. Go back. Erase this too. I just don't have enough room there. Okay. So this is going to be A1 is 1/3 time. Oh, I shouldn't have erased all that, should I? Okay. The integral of dx over, I had to remember which one went with what, and I forgot that. I think it's x minus 5, wasn't it? A1 was over x minus 5? Yeah. Minus 1/3 the integral of dx over x minus 2. Okay? So since I've got those in place, now I'll erase these. Hopefully I won't need those again. And what do we have?
Good question.
Yes.
Since this one over here in x plus minus 2 area, wouldn't that 1/3 be negative also?
Okay. I thought you told me what A1 and A2 were, didn't you?
Yeah, A2 is negative 3.
It's negative 1/3, and the A1 was
1/3.
Positive 1/3.
Yeah.
Okay, and A1 went with the x minus 5, did you tell me? Yeah, so it's 1/3 over x. In fact, here it is right here. This is what we got there. They put the x minus 2 in front, we put the x minus 5 in front. It doesn't really matter. So that is a minus 1/3 over the x minus 2 and a plus 1/3 over the x minus 5, right?
Yeah, I just didn't, I thought we normally just subtracted 2 functions, but we add them. So I get it.
Okay?
Yeah.
All right. Okay, good deal. Can we do those integrations? antiderivative of 1 over x minus 5. The natural log of, okay. Now, when you're dealing with natural logs, be sure you put absolute value bars, because you cannot take the log of a negative number at all. So that will be absolute value x minus 5 minus 1/3 what? Log of x minus 2. Okay? Now, that's perfectly hunky-dory to do. Now, what I haven't done is written down my plus c. And let's see where they do it. They leave it right there and put a plus c. Okay? Which is perfectly okay to do. Now, I did A1 and A2. They did A and B. It doesn't matter what you call them. In their example, they did A1, A2, A3, up to AN. Then when they actually did it, they did A plus A and B. It doesn't matter what you name it, whatever it is, okay? So there's the answer they have. Let me suggest to you a few other answers you could have, okay? This is where, remember a log, you can raise that to a power. You could write this as the log of absolute value x minus 5 to the 1/3 power, right? So something in front of a log can be moved as the exponent of the thing inside the log. And this could similarly be, depends on how you want to do it, minus the log absolute value x minus 2 to the 1/3 power, okay, plus c, okay? But then you could say this is the difference of two logs is the log of the quotient, right? There's another property of logarithm. Remember that one? Okay, so that would be the log of absolute value x minus 5 over x minus 2. And since they have the same base, to the 1/3 power, okay? All right, plus c. So there's a bunch of different answers you could write, okay? And they're all correct, all perfectly fine. And actually what you could have done was made this a log c. That would have been the right answer, right? So log c is a constant, just like any other constant, right? Log c is positive, okay? But if you had done that, then you could have had this c inside here, because those are things multiplied together. So you could have log of c x minus 8 over x minus 5 over x minus 2 to the 1/3 power. There's a bunch of ways you could write that answer. And a lot of the times, the calculus is pretty easy, than trying to figure out which way the book wants the answer is a little bit harder. And that's why if you give me an answer and you show your work, and I work with it and find out it's the same answer as the one given in the key, you get full credit for it. Okay? So I suggest you do that. Don't, whatever. All right. Now, what you may or may not have noticed was this box in the middle of this was what we got when we did our partial fractions. Minus 1/3 over this plus 1/3 over that. And then we integrated up to that. Okay. All right, here I think is example 2. Let me blow it up and see for sure if it is. It's so small I can hardly read it. I hit the wrong key here. Okay. Evaluate this. X squared plus 2 over x minus 1 times 2x minus 8 times x plus 2. it really irritates me for them to give you problems like this, because that can be simplified. Factor out a 1/2 and leave it at x minus 4. There's no reason to have a factor that's not completely factored. If you had a 1/2 out front, then that's the same as this stuff. And it makes the rest of the problem so much easier to do. They go through all sorts of ugly gyrations to make theirs work. And it's just not necessary. Factor out the 1/2 to begin with, and go from there. So that's what I'm going to do. But of course I can't write on it, unless you want to see it the way the book did it. I don't care.
Factor 1/2, want to change all the other ones?
Say again there?
Want to change all the other?
No, okay. We're talking about factors here, right? This has a factor of 2. This would be x minus 1 times 2x minus 8 times x minus 2. If you factor this to be 2 times x minus 4, it would be x minus 1 times 2 times x minus 4 times x plus 2, right? Same thing, right? You just factored it further. And then pull the 2 over here and factor it out in front of all that, and then just a 1/2 times all that. Yeah, as long as that becomes an x minus 4. It is, that's the same thing. It's just, they didn't factor completely and they should have. Okay. Now, it will mess up how the answers look, but if you work with them, you'll find out they are equivalent answers. It's just, I think, doing it this way is a little bit cleaner. Okay? But I can't write on this until I shrink it back down again. So, our integral, sorry, Sandman is really working overtime in here. Is now a 1/2 x squared plus 2 over x minus 1 times x minus 4 times x plus 2 dx. Now, I should have been saying this. I think of it every time, but then by the time I get to the point in the problem, I forget to say it. Okay? You don't, yeah, some of you have your books there, but some don't. If you'll notice this, example 1, you just had 1 over x squared. Obviously a proper rational expression. Okay, this one, and the one we did earlier, before we got there, that 5x squared minus x over x plus 1 times x minus 2 times x minus 3. Degree of the numerator was 2, degree of the denominator was 3, because you have x times x times x is x cubed. This one also is proper, because you have degree 3 down here, x times x times x would be x cubed, and the x squared up here, so that's proper. We don't have to divide or anything. We got it done, okay? Now, what would be your next step? Do you have a next step? Please have a next step. What would it be? X squared plus 2 over x minus 1 times x minus 4 times x plus 2. Okay? That would be A, you said, over x minus 1. How about B? Yeah. X minus 4. Okay? We want that to happen. To decompose that pretty complicated looking thing up there into a something we can work with, partial fractions. what would we do next? Okay, and that would be x minus 1 times x minus 4 times x plus 2. This times x minus 1 times x minus 4 times x plus 2. This one times x minus 1 times x minus 4 times x plus 2. And this is times x minus 1 times x minus 4 times x plus 2. Okay. Now what? Oh. Get rid of any common factors. X minus 2, x minus 1 of x minus 1, x minus 4 of x minus 4, x plus 2 of x plus 2. That's nice. X minus 1's here, x minus 4 is there, and x plus 2's there. Okay? Now what? Let x equal 4. Sounds like a wiener. Okay? What does your left-hand side become? 18 is equal to right-hand side? A little louder. A2, you said? Huh? Okay, you use A2 rather than B? It's okay. It's fine. Okay, I just wanted to make sure I understood you. A2, we'll call it A2. That's fine. Times.
Times
3 times.
6.
Yeah, 6. Okay. So what's your A2 or your B? Yep. Okay, A2 or B would be equal to 1. Okay, I like it. Next. -2 will do. Okay. And then what do you have on the left-hand side? 6 is equal to, what's on the right-hand side?
Okay, so when it comes to this part, how do you choose between A, B, and C?
Second.
How do you choose between those?
How do I choose between them?
Yeah.
Okay. If you say x equals -2, okay, x equals -2 makes that go to 0, right? So x equals -2 makes this one go to 0. Notice the sign there. You got it. Okay. Now, x equals -2, it chooses it for you. C is the only one left standing, right?
Okay, I got it.
Right?
Yeah.
Is that what you meant?
Yeah.
Okay, yeah. That's why we chose the -2, right? To have a 0. Some people like to choose 1s, and then you don't get rid of them. And then you have 3 equations, 3 unknowns, and they're really challenging to solve. But some people like challenges. Yeah. Okay. All right. All right. So if x equals -2, you got 6 on the left-hand side. What do you have left on the right-hand side? Okay, A3, we're going back to that, okay.
Times -3.
-3 times.
Is that plus 4?
I think it's a -4 if I'm not mistaken.
Times
-7. I'm not liking this one at all, are you? Did I do something wrong here? I think we're okay. Ooh.
-6.
What's that?
-6.
Yeah, you're -6. Whew. Good, Theo, thank you. I didn't think that's a -6. Why am I listening? Never mind. Okay. So what's A3 or C equal to? Is what?
1/3.
Yep. 1/3. Okay. Because this is a +8. These become plus. So plus and plus. Okay. These go out. Perfect. Okay. One more. Those are so much fun. What's?
1,
X equal 1. Okay. What would that be then?
3,
3 is equal to
A1,
A1.
-3,
A1 is equal -1/3. Okay. Now, I just don't have enough room on this little bitty screen here. Okay. So this integral becomes 1/2 the integral of, well, let's see. -1/3 the integral of dx over x minus 1, right? That's how we broke it down. Okay. Plus 1 times the integral of dx over x minus 4, right? Plus 1/3 the integral of dx over x plus 2, right? By that? Okay. Your A1 was that one. That was a -1/3. Your A2 was 1. So that was over x minus 4. And A3 was 1/3. And that's over x plus 2. Let's see. Whatever you want to call it. Okay? Now I think we can erase some stuff, right? Okay. That was all you needed. You needed all that to get your forms that you were after. You've gotten them now. I'm so hungry I can hardly stand it. Like I said, I did a lot of work this weekend, and I think I got the old metabolism riled up. Okay, I may come back and erase some more. Let's see what we can do with that. Okay, so we have a 1/2 out front times what? Integrate that. Integrating this right here. Put the 1/2 out front. That and the left. Log, I'll put absolute value x minus 1. Okay, you left off something. Okay, so that'll be, you want that in front of the log?
Yeah.
Okay, that'll be fine. -1/3 log x minus 1 if you look at their answers then, okay, they get a, and, let's see, I forgot that. Okay, they get a minus 1/6 log of x minus 1. Bingo, right. Plus 1/2 of log of 2x minus 8. Well, we don't quite have that. We have x minus 4 plus 1/6, 1/2 times 1/6 log x plus 2 plus c. Okay? Now, how does ours differ from theirs? Just that term right there. They had a 1/2 log absolute value 2x minus 8, right? I can't find it. Yeah. Right? That's their middle term that differs from ours, right? Well, again, I would say that factors as 1/2 times the log of 2 times x minus 4, right? And this would be 1/2 log 2 plus 1/2 log x minus 4. But guess what? 1/2 log 2 is just a constant. So that's incorporated into our constant. So yeah, they're the same answers. Even though they look different, they are the same. Okay? Because then it was just like ours. Okay? Wherever it is, right up there. Okay. So there's no reason to carry around, extra factors that you don't need to. Go on and factor it out completely. All right. Let's see what they do next. This was part of what they did, and they used A's, B's, and C's rather than A1s, A2, and A3s. Okay? And for some reason, and they multiplied through by the factors, and they got this and this and this. Yeah. That was the same thing we did in an earlier step. Okay? If you look at the, I think I may have erased that, but let's just see. Yeah, I think I did erase it. But yeah, that's basically the same thing we had there. Okay? And so nothing new there. Now, I think the next slide, no. So they go back and write that down. The only difference is we had this, and we had 1/2 out front and 1 over x minus 4 here, which is perfectly fine. You see everything pans out well that way. All right, this then is example 3. Any questions on example 2 before we leave? Okay, example 3. Evaluate this one. The integral of 3x minus 9 over x minus 1 times x plus 2 squared. Okay, yeah. All right, now what's different in this case is that we have a repeated factor. Now remember back before we said all of the roots for that needed to be distinct. This one isn't. It's a repeated factor of x plus 2, which would be a root of x equal -2. That would be a repeated root there, a multiplicity of 2. Okay. Now, what you do differently here, you start out just the same as you did before. Now this sort of seems, at least to me, it seems a little counterintuitive. But here's where you go from here. Now, first thing I would do, I would factor out the 3. Okay? Why make it more difficult than it needs to be? Make that 3 times the integral of x minus 9 over this stuff, x minus 1 times x plus 2 squared dx. Okay? X minus 3. You were going to say that, weren't you? Thank you. You need to watch me. Whoops. Okay. The old gray cells ain't what they used to be. Okay. So, what would be your guess of what to do next?
We have 3.
What's that?
Technically, we have 3 functions in the bottom.
Yeah.
Minus 1 and 2 times.
Yeah. We have x minus 3 over, and did you say write it as 3 factors?
Yeah.
Okay. X minus 1 times x plus 2 times x plus 2. Is that what you meant? Okay, that's perfectly legal to do. And that's equal to what? You go back to that. I should never have done that. Okay, a1 over x minus 1. Is that what you were going to do?
Yeah.
Okay. X plus 2? Okay. Okay. Now that is a really good guess to do, but let me point something out. Those are the same thing. You can make that a2 plus a3 over x plus 2, and that's just 1 not 2. Okay? Here's what you do. Keep that one to the first power, this one to the second power. That's what you do. And there's nothing intuitive to me that indicates you should do that. But if you do it, it works. Okay? Because if you did do it the other way, that's just one constant. It's not 2. Because that would be a2 plus a3 over x plus 2, and you still only have 1. You need 3, though, because you have 3 factors. So the first time, anytime you have a repeated factor, you do a separate constant over the first power, second power, third power until you get up to whatever your maximum power is. So that's the rule. Why they don't tell you the rule before they make you do it, but that's what you got to do. Okay? So, what next?
Find the numbers.
Okay, and what is that? X plus 1. Okay. X minus 1 times plus 2 times. And you could write it as x plus 2 squared. It doesn't really matter. X minus 1 times. And this one I will write that way because I don't have much room. Okay. Got it? Now what?
Now you put the numbers.
Say again?
Now you divide the numbers.
Okay, not yet. You divide out. X minus 1s go out. X plus 2 go out. X plus 2 goes out. X minus 1 goes out. X plus 2, one of those goes out. And here, both of them go out. Okay. Now, what numbers do you want to let them be?
1.
Let x equal 1. What's your left-hand side become? Negative 2, is that what I heard? Okay. Negative 2 is equal to A1
3 times 3, so
9, okay, which would imply
1/3.
isn't it more like 2 ninths? Huh?
Does that have to be negative 2 ninths?
Say again?
Does it have to be negative 2 ninths?
Well, tell me how you got 1/3.
Uh,
I may argue with you, but
I don't know.
did I do something wrong here?
No, you're right, I'm confused.
Okay. Boy, this new calculus always throws me off, okay? This will be what?
Negative 2
2
ninths.
ninths, okay? Then let x equal
Negative 2.
-2. What's the left-hand side become?
Negative 5.
-5 is equal to
8/3.
A3 times -3. Okay, so what does A3 become? 5/3. Okay. Now, we've run out of things to let, haven't we? Okay? We still have no clue on A2, do we? So what we have to do at this point is plug in what A1 is, plug in what A3 is, and see what we've got left. Okay? The left-hand side becomes x minus 3, right? And that's equal to A1 was minus 2 ninths, negative 2 ninths times x plus 2 times x plus 2, right? Plus A2 times x minus 1 times x plus 2. Plus 5/3 times x minus 1. I think that's right, isn't it? Agreed? All right, this is the old hard way, okay? X plus 2 times x plus 2 is x squared plus 4x plus 4 multiplied by minus 2 ninths, that's minus 2 ninths here, minus 8 ninths here, minus 8 ninths there, right? Plus A2 times x squared plus x minus 2. Is that right? Got it? Plus 5/3 x, it is minus 5/3. Okay. Oh, what a joy. I need a whole lot more room. I just don't have anywhere to put it, though. All right, what I'm going to do is erase what I can. Get rid of those because they're out of there. rid of that one because that one's out of that. Oh, that's not what I wanted. I'm going to put my x, just for future references, that was over x minus 1. Right? I think so. Yeah. This is going to be a little messy. In fact, very messy. My pen is not erasing properly. I don't know why it won't erase. Yeah. No. Okay. Now it erased. All right. Okay. Okay. I'm going to rewrite this. A1 is equal to negative 2/9, and A2 is equal to 5. No, A3 is equal to 5/3. Okay, get those out of the way. Now I think I can erase the rest of it. Down to here. Okay. Now, I hope I don't need that other part. Okay, let's see what we've got here now. We got minus 2/9 plus A2, because these are the coefficients of A squared, right? This is equal to A minus 3. I don't know how I lost mine. A minus 3. Right? How did I lose it? I don't know. That's x minus 3. I can't even talk. Okay. Okay. Now this is a lot of mess to give you a very simple answer. Okay? Because this says that if you look at the x squared terms, you get a, you don't have any x squared here, right? It's a 0 is equal to minus 2/9 plus A2. Because none of the rest of these have x squared, right? So this tells us A2 is equal to 2/9, right? Because the x squared term, 0, has to equal minus 2/9 x squared plus A2 x squared. A2 minus is positive 2/9. Yeah. A2 is equal to positive 2/9. So A2 is equal to 2/9. Okay? So now our integral up here is 3 times minus 2/9, the integral of dx over a minus 1. Say, it's not an a, it's an x. I write a d. X minus 1. La la land, okay? Plus 5/3 times the integral of dx over x plus 2 minus, no. I used the wrong one. That's the 2/9. I don't know. This thing is so screwed up. There we go. Plus 2/9. X. Yeah. And then plus 5/3. That's the A3. The integral of dx over x plus 2 squared. Okay. I think I can get rid of all this other stuff. I sure hope so. Sorry, this is taking so long. These things can get tedious at times, especially if you have a very small screen that you have to erase every other line. Okay. So this is 3 times, okay, I'm going to go and multiply through by 3, if that's all right. That would be minus 2/3. What's the integral of dx over x minus 1? Log absolute value x minus 1. Very good. That should be a straight line. Plus 2/3 log absolute value x plus 2 plus 5. Now that's where I think I'm having problems. No. Okay. Now, what is the integral of that? No longer a log. Substitution. Sounds good. What would you substitute? That's what? U equal x plus 2. You okay with that? Then du is equal to? Dx. Okay? You're trying to make it a lot harder than it is, okay? So what do we have now? I'm going to leave off the thing in front. That would be the integral of du over u squared, which you could write as the integral of u to the negative 2 du, and that integral would then be, I think that's what you were doing,
would be u over -2.
What's that?
Over -2.
Okay, over -1.
Oh, -1. Okay, I got it now.
Right?
Yes.
And that's why I put the minus in front, because it's 1 over, yeah. Okay? Plus c, but we have plus c for all of it. And then what was the u?
X plus 2.
Yeah, so it's plus 5, or actually becomes a minus 5 over x plus 2. Then you can have your plus c. I think that should be the answer. I've got to find it. There it is. Negative 2/3 log absolute value x minus 1 plus 2/3 log, absolute value x plus 2, minus 5 over x plus 2, plus c. Very good. All right. Right? Now, these are just some intermediate steps here that they did. I think we've already done, but let's just see them. This is the left-hand side. They didn't factor out the 3, I did. And they got, yeah, this is when they divided out the denominator. Okay, multiply through all these common denominator. This is what they wound up with, which is what we got, I think. And then this is their final translating the first integrand to the partial fractions, and that's exactly what we got as well, right? Okay. And then when they integrated it, but this is moving on to something else. So,
Quick question.
yes.
How does this have any application in real life?
When you're trying to do integrating things that you don't have, well, for instance, if your integral turned out to be any of these rational expressions, the only way you can integrate it is by that. So if in your real life you're having to do some integration, now you're both engineers, and engineers love to make tables and let the tables do most of the work. I didn't say that, did I? Okay.
I mean, I did have a teacher that she said that we have to learn all of this to be able to use the tables, basically. That's what she said. You gotta go to the front time for you to be able to use the easy tables.
Right.
We're not worthy enough because we have to show.
What's that?
Is it like, I don't know, I was trying to get what you were saying.
Yeah.
It's like we can't just use the tables and
Right.
make it easy.
You could, but the thing is, if you are using the table, but you screw that up sort of, you have no way of having an idea whether you are anywhere close to the right answer or not. If you know where the tables came from, then you can say, no, that doesn't seem right. Oh yeah, there's an error there. You know, it's kind of like if the only way that you can take a square root of 17 is punch it on a calculator, but you punch it incorrectly and you come up with something 5.7. Okay, square root of 17 is 5.7. Wait, no, it isn't. Square root of 17 is just a little bit more than 4. So I hit a wrong key somewhere, you know. But if you don't know what the process should be, then you're at the mercy of a table or something like that you don't know. But there are other times where, I mean, just like any of these techniques, if all you're going to do is look up at a table, then why are we even doing any of this, you know? Well, it's the exercise of knowing what things should be and whether they're coming out the way they should be, you know. I think that's the best answer I can come up with. And I think the design of that question was to use up the rest of our time so we wouldn't have a chance for another example. Well done. Okay. We will start next time then with example 4. Okay. Let me get rid of this mark. What's that? Print? Yeah. Yeah, I was going to say the library. Don't you need a little card or something?
You do they have like a little machine. You put one of these cards, which costs $1 just for the card. And then
If you don't have the card, you can't.
But I mean, that's all the cards down there. It's like a little machine. It's like you put $1, it gives you the card, and you got another dollar from credit.
Is that in cash?
Yeah, because
Okay, and it doesn't use the whole dollar. You have left over on the card. And later, if you need to print something else, you've got the card already.
I think I have a dollar. No, I have 95 cents.
Okay. Let me give you a few homework exercises. I know you won't want to leave without those. I think you can do 1 or 3 or both. Any of the odds, 5 or 7 or both. And then any of the odds 9 through 21. And we'll pick up the rest of those next time.
I got it.
I think that's